Hello friends, welcome back to my channel. Today I'm continuing my discussion on distillation. This is part 13 of my discussion on distillation, and today I'll be discussing uh, one numerical that is based on simple distillation. In my previous video also I had discussed one numerical. Now what I'm going to do, I'll be discussing the same numerical. In my last video I have discussed how to solve it graphically. Today in this video I'll be discussing how to solve the equation, Rayleigh's equation. You know, Rayleigh's equation is the governing equation for simple distillation. So today I'll show you how you can solve Rayleigh's equation analytically and then get the final solution. In my previous video I have discussed how to solve this Rayleigh's equation graphically. Okay, so the point is I'll discuss the same numerical, the one that I discussed in my previous video, but this time I will be solving Rayleigh's equation analytically. So let us start the discussion. So the numerical statement, now this is second, so I'm calling it as numerical number 2. Now the statement goes like this: 120 moles of benzene and toluene solution containing 45 mole percent of benzene is subjected to a differential distillation at 1 atmosphere pressure. At the end of the operation, the composition of benzene in the residue is 29 mole percent or 29% mole. Calculate the total moles of the mixture distilled, and in this case benzene is the more volatile component and average value of the relative volatility is 2.16. Okay, the statement is same. As I said, we will solve the same numerical, but this time we will be solving Rayleigh's equation analytically. For those of you who have not yet seen that video, my previous video, I'm giving link to that video in the description section. You please watch that. Okay, what are the given things? Let us note down. First, we have the feed solution that is known to us. So the feed solution is a solution of benzene. Let us call that as A, and toluene, that let us call that as B. The quantity of the feed solution is 120 moles, and then benzene is the more volatile component. Again, this is given. 45% mole of benzene is in the feed. So from all this information we can note two things. One is we can note F is given to us, it is 120 moles, and then XF is also given, it is 0.45. Since mole percent of benzene in the feed is 45, if you divide that by 100 you'll get mole fraction, and we denote mole fraction by XF, so XF is 0.45. Okay, so let us move ahead. Further, the process that is involved in this case is differential distillation. So the feed solution is to be differentially distilled. Pressure is given, pressure is 1 atmosphere. At the end, the residue is to contain 29% mole of benzene. So finally, in the residue, mole percent of benzene is 29. So from this, we can collect these things. Pressure, P is 1 atmosphere, and then XW, that is mole fraction of benzene in the residue, it is 0.29. 29%, 29 divided by 100, that gives us 0.29. So XW is 0.29. Okay, so let us move ahead. Then any other parameter, is any other parameter given in the statement? Yes, they have given us relative volatility of the solution. It is 2.16. That is alpha AB is 2.16. Now what is the objective? The objective is to find the total moles of the feed solution that gets distilled. That is, we are supposed to find out D. Okay. So after noting what things are given to us and what are we supposed to find out, now let us go for the solution. Okay. Solution. What is the approach for this particular numerical? We are going to get D. The objective is to get D, and D will be achieved by using the following equation. F is equal to D plus W. What is this? This is steady state material balance. Feed will either be converted to distillate or the residue. So in this case, F is given to us and we need to calculate W, and W will be calculated by using Rayleigh's equation. Okay, what is Rayleigh's equation? Rayleigh's equation is ln of F by W is equal to integration from xw to xf dx upon y minus x. Last time we had solved this integral graphically, and now we are going to solve it analytically. That is the difference. And we'll also compare the results. Okay, so the integral on this on the RHS of this equation, we are going to solve it analytically. How? How are we going to do that? In order to solve this analytically, we need to know equation for y in terms of x. So that's what I'm saying. The integral on the RHS is solved analytically by using an equation for y in terms of x. What is that equation? The equation is known to us. The equation is y is equal to alpha abx divided by 1 plus alpha ab minus 1 into x. So idea is, in place of y, we will be using this. And we can do that because alpha ab is known to us. So if you use alpha ab in this equation and simplify it, we'll be getting a simple equation for y, that is in terms of x, and then we can put this equation in the integral and then integrate it analytically. Okay, so let us do that. So what are the steps involved? So first we will solve the integral analytically. Then after uh, getting integral, we are going to find out W, and then from W we are going to, once you get W, we will be finding out D. Three steps are involved. Let us go for the first step, solving the integral analytically. What is the integral? Integral is, let us denote that by I. So integral is I is equal to integration from xw to xf of dx upon y minus x. Uh, so now, as we have decided, we are going to use equation for y. So y is alpha abx divided by 1 plus alpha ab minus 1 into x. Alpha ab is known to us, it is 2.16. So if you use that value, you have y is equal to 2.16x divided by 1 plus 2.16 minus 1 into x. That is y is equal to 2.16x plus 1.16x. 2.16 minus 1 is 1.16x. Okay. So we will be using this equation for y in the integral. Okay, so let us do that. So we are solving the integral. From the previous slide, we have got this, or we have the integral I is equal to integration from xw to xf dx upon y minus x. Now equation for y is 2.16x divided by 1 plus 1.16x. So we will use this equation for y in the integral. So therefore you have I is equal to integration from xw to xf dx upon 2.16x divided by 1 plus 1.16x minus x. So in place of y, I have used this equation. Okay, let us simplify it. So therefore I will be integration from xw to xf dx upon 2.16x minus 1 plus 1.816x into x divided by 1 plus 1.16x. So I have simplified the term in the denominator. Further, I will be equal to integration from xw to xf. Again, after simplifying, uh, the next step for this will be 1 plus 1.16x divided by 2.16x minus x minus 1.16x square dx. So I have simplified the term in the denominator. Further, I will be equal to integration from xw to xf 1 plus 1.16x dx divided by 2.16x minus x minus 1.16x square. Okay, so one more time I have written the equation. Now next what is done, 2.16x minus x is 1.16x. That's why you have this. Therefore I will be equal to integration from xw to xf 1 plus 1.16x dx divided by 1.16x minus 1.16x square. In the next step, what we can do in the denominator, you can check 1.16x, it can be taken out as a common term. So therefore you have integration from xw to xf 1 plus 1.16x dx divided by 1.16x into 1 minus x. Now over here I have taken 1.16x common in the denominator. Okay, next. So previously we had got this I is equal to integration from xw to xf 1 plus 1.16x divided by 1.16x into 1 minus x. In the next step, what I have done, I have separated the denominator. So if I do that, I will get I is equal to integration from xw to xf of 1 upon 1.161 into 1 minus x. So now the denominator is separated, plus 1.16x divided by 1.16x into 1 minus x dx. Okay, so I have used one approach to get the solution, analytical solution. You can simplify this in some other way, there is not a problem. The basic idea is why we have replaced in terms of x, and then we are solving the integral analytically. Okay, next, now I'll write it like this. So what is going to happen, in the second term 1.16x is going to get cancelled. So that's why you have I is equal to integration from xw to xf 1 upon 1.16 into 1 minus x plus 1 upon 1 minus x dx. 1 minus 1.16x has cancelled out. Okay, next step is I'll separate the integral so that I will have two integral terms in that way. Therefore, I will be equal to integration from xw to xf dx upon 1.16x into 1 minus x, first integral term, and the second one will be plus integration from xw to xf dx upon 1 minus x. Okay, now let me call the first integral as I1. We are going to solve it separately. We are going to solve it by using integration by parts. Okay, so for time being I'm denoting it as I1. So I will be equal to I1 plus integration from xw to xf dx upon 1 minus x. Let us call this as equation 1. So we are going to refer it once again after getting I1. So I1 is solved by using integration by parts. So I1 is integration from xw to xf dx upon 1.16x into 1 minus x. Now let us simplify this term. So you have this term 1 upon 1.16x into 1 minus x. So I'll have two parts for this. You must be knowing how to solve integration by parts. So that is a upon 1.16x plus b upon 1 minus x. Okay. Now our task is to get a and b. So once you get a and b, you can easily integrate this term a upon 1.16x, and this term also you can easily integrate. Okay. So the net result is we are going to get the solution for this term, integration of this term. Okay. So let us move ahead. So from the previous slide, we had got this. We had two parts. 1 upon 1.16x into 1 minus x is equal to a upon 1.16x plus b upon 1.16 b upon 1 minus x. Okay, so what I will do, I will simplify on the right hand side. So that is 1 upon 1.16x into 1 minus x, that is equal to a into 1 minus x plus b into 1.16x divided by 1.16x into 1 minus x. Okay, I have simplified on the right hand side. So in the next step, so 1.16x into 1 minus x, the term in the denominator on both the side, that is going to get cancelled. So you have 1 is equal to a into 1 minus x plus 1.16 into b into x. Okay, so let us call this as equation 2. Now our task is we are supposed to get a and b. Okay, so the approach is, in order to get a, what we are going to do, we are going to put the term that is in the denominator, uh, the part which has a in it. So in this case, first, in order to get a, what I am going to do, I will put 1.16x is equal to 0. Okay, so I am doing 1.16x is equal to 0 in equation 2. In other words, I'll be putting x is equal to 0. 1.16 into x is equal to 0. That means x is equal to 0. Okay, so therefore I have 1 is equal to a into 1 minus 0. Now x is replaced with 0 plus 1.16 into b, x is replaced with 0. So this will be 0, and this a 1 minus 0 is 1. So it will be having 1 is equal to a into 1 plus 0, which gives us a as 1. Okay, so now we have got the value for a. Now let us get the value for b. So for getting value for b, the term in the denominator which has b in it, we are going to replace it, we are going to equate it to 0. Okay, so that means 1 minus x is 0, which is nothing but x is equal to 1. So if I put x is equal to 1 in equation number 2, I'll be getting 1 is equal to a into 1 minus 1, x is replaced with 1, plus 1.16 into b into 1, x is replaced with 1. Okay, so in the next step you have 1 is equal to 1 minus 1 is 0, so a into 0 plus 1.16 into b, that is 1.16 b is equal to 1 and b is equal to 1 upon 1.16, which gives us b as 0.862. Okay, so in this way we have got values for both the constants. A is 1 and b is 0.862. Okay, so now you have two simple terms which can be easily integrated, and the result will be we are going to get integration for the complicated term, not that complicated but somewhat complicated term. Okay, so let us do it. So previously we have got this, we had two parts, 1 upon 1.16 into 1 minus x is equal to a upon 1.16x plus b upon 1 minus x, and now we have got values for a and b. A is 1, b is 0.862. Okay, now let us use the values. So it will be 1 upon 1.16x into 1 minus x, that is equal to 1 upon 1.6x plus 0.862 divided by 1 minus x. Now let us integrate it. So integration from xw to xf dx upon 1.16x into 1 minus x, that is equal to integration from xw to xf dx upon 1.16x plus integration from xw to xf 0.862 divided by 1 minus x into dx. Okay, so we have integrated the two terms. Now I1 is, we started with uh, this you can say note assumption. I1 is integration from xw to xf dx upon 1.16x into 1 minus x. So therefore I1 will be equal to, now I1 is equal to the result that we have got. I1 will be equal to integration from xw to xf dx upon 1.16x plus integration from xw to xf 0.862 divided by 1 minus x into dx. Okay. Now equation 1 which we had earlier written, that is I is equal to I1 plus integration from xw to xf dx upon 1 minus x. Okay. Now let us simplify it further. Okay, now let us continue further. So from the previous slide, we had I1 is equal to integration from xw to xf dx upon 1.16x plus integration from xw to xf 0.862 divided by 1 minus x into dx. Equation 1 is this thing, I is equal to I1 plus integration from xw to xf dx upon 1 minus x. Now let us put I1 in the equation. So you have I is equal to integration from xw to xf dx upon 1.16x plus integration from xw to xf 0.862 divided by 1 minus x into dx plus integration from xw to xf dx upon 1 minus x. That is I is equal to integration from xw to xf dx upon 1.16x. Now 0.862 I have taken out of the integral, so this will be plus 0.862 integration from xw to xf dx upon 1 minus x plus integration from xw to xf dx upon 1 minus x. So this is addition of two terms that has the integral same integral in it. So it is like addition of two terms. So point, like it is like 0.862 m plus m, so it will be 1.862 m. Are you understanding it? So I will be equal to integration from xw to xf dx upon 1.16x. So the addition of this two will give us 1.862 integration from xw to xf dx upon 1 minus x. Okay, then constant, let us take the constants out. For the first term, it will be, or the result will be I is equal to 1 upon 1.16 integration from xw to xf dx upon x plus 1.862 integration from xw to xf dx upon 1 minus x. Okay, so you must have seen, or you must have observed that we have converted the term that was a little bit difficult to integrate into two simple terms which can be easily integrated. So that's why we had used integration by parts. Okay, now you can easily evaluate this integral. Okay, so let us continue with it. We have I is equal to 1 upon 1.16 integration from xw to xf dx upon x plus 1.862 integration from xw to xf dx upon 1 minus x. So now let us use the limits. You know, xw is 0.29, xf is 0.45. Therefore, you have I is equal to integration I is equal to 1 upon 1.16 integration from 0.29 to 0.45 dx upon x plus 1.862 integration from 0.29 to 0.45 dx upon 1 minus x. As we know, xf is 0.45 and xw is 0.29. Okay, now integration of 1 upon x is ln of x. Therefore, you have I is equal to 1 upon 1.16x into ln of x, and the limits are from 0.29 to 0.45. Then integration of 1 upon 1 minus x will be ln of 1 minus x divided by coefficient of x. Now in this case, coefficient of x is minus 1. So it will be 1.862 into ln of 1 minus x divided by minus 1, and then limits are from 0.29 to 0.45. Therefore, I is equal to 1 upon 1.16 into ln of x with limits 0.29 to 0.45. Now this minus plus is becomes minus, so minus 1.862 ln of 1 minus x from limits 0.29 to 0.45. Okay, so we have got this equation. I is equal to 1 upon 1.16 ln of x with limits 0.29 to 0.45 minus 1.862 ln of 1 minus x with limits 0.29 to 0.45. Now let us use the limits. So it will be 1 upon 1.16 ln of 0.45 minus ln of 0.29 upper limit minus lower limit minus 1.862 ln of 1 minus 0.45 minus ln of 1 minus 0.29. Ln of 1 minus 0.45 minus ln of 1 minus 0.29. Again, we have used the limits. So it will be 1 upon 1.16. Ln of 0.45 is minus 0.8 minus ln of 0.29 is minus 1.24 minus 1.862. Ln of 1 minus 0.45 is minus 0.6 minus ln of 1 minus 0.29 is minus 0.34. Okay, so that gives us I is equal to 1 upon 1.16 into 0.144 minus 1.862 into minus 0.26. Okay, so that gives us I is equal to 0.38 plus 0.48, and which gives us I is equal to 0.86. Now we have got the value of the integral. So I is 0.86. That is nothing but integration from xw to xf dx upon y minus x. This is I. Therefore, now you have the value of the integral. Integration from xw to xf dx upon 1 y minus x, that is equal to 0.86. Okay, and if you remember, graphically we had got this as 0.845. You can refer my earlier video. There I have solved this integral graphically, and the value obtained at that time was 0.845, and analytically we are getting it as 0.86. So Rayleigh's equation is integration from xw to xf dx upon y minus x, that is equal to ln of f by w. Now we know the integral, so let us use the value. That is ln of f by w is 0.86. F is given, f is 120 moles, so ln of 120 by w is 0.86. So 120 by w is e raised to 0.86, that is 120 by w is 2.36, that is 120 by 2.36 is W. That gives us W as 50.85 moles. 50.85 moles. Now using the total material balance, which is F is equal to D plus W, we have got W. So it will be 120, that is equal to D plus 50.85. That gives us D as 120 minus 50.85. That is D is equal to 69.15 moles. And finally, thus we have achieved our objective. We have got the final answer. Therefore, the total moles of the feed solution that gets distilled are 69.15. Okay, so that is the final answer. You please watch my earlier video where I have solved this integral graphically and compare the results for yourselves. Okay, you can check how close we are in by the two approaches. Okay, so with this I end my discussion for today's video. Here I have told you how to solve Rayleigh's equation analytically. I hope this is useful to us, useful to you, and we'll continue to watch my videos. Please subscribe to my channel. Thanks for watching. Subscribe to my YouTube channel. Please tell your friends, ask your friends to subscribe to my channel. Thanks for watching. For now, have a good day and let us meet once again in my next video. Thank you. Bye bye.